Section 3.4, real zeros of polynomials. One of the main sections and more important sections of Chapter 3 is being able to find zeros of polynomials. If you think back to Section 3.2, remember zeros are the same thing as x-intercepts. And if we need to graph a polynomial, finding x-intercepts is extremely important. And so in order to find x-intercepts, we need to find the zeros. And as we talked about in the last section, 3.3, sometimes finding zeros or factors of polynomials can be challenging if it doesn't factor using traditional factoring techniques. We have to use synthetic division or long division in order to find factors. And so that's what this section and the next section, 3.5, are about, are finding real zeros of polynomials using synthetic division. So you can see we have a couple of learning targets here. Rational zeros theorem, and then finding all rational and real zeros of the polynomials, all leading up to being able to graph a polynomial. So let's get into it. Now, real quick, just before we get into this lesson, rational zeros, real zeros, and then the next section, section 3.5, is titled complex zeros. Just a real quick aside, I suppose, there's, in the number system, there's real numbers. Let's do this. There's real numbers. And real numbers actually encompass several different sets of numbers. So if we think of a Venn diagram, for example, so real numbers come in two different sets now. So we have rational numbers, and we have irrational. So we have rational and irrational. And then within rational, technically, and this is not something that's super important to the lesson, but rational numbers, you have a smaller subset of rational numbers called integers. Integers are whole numbers. And then you have a smaller subset of integers called natural numbers. Those are positive integers. Anyway, the main point I'm trying to make is this lesson is called real zeros of polynomials. And real zeros can either be rational numbers or irrational numbers. Rational numbers are numbers that can be written as fractions. That's what the word ratio means. So rational numbers means numbers that can be written as fractions. Irrational numbers are numbers that cannot be written as a fraction, like pi, 3.14, or the square root of 2. These are all irrational numbers that can't be written as fractions. And another important thing, real numbers actually exist on the real number line. So there is a value on the real number line for irrational numbers, like pi is 3.14, or the square root of 2 is 1.41. So you can actually find those values on the real number line. Same with rational values. Anything that can be written as a fraction has a decimal that can be found on the real number line. So this is what is meant by real zeros of polynomials. And the first subtopic, rational zeros, these are zeros or x-intercepts where the values are rational numbers, meaning they can be written as fractions. Okay. So the first subtopic here, rational zeros theorem. This is the definition that we saw in section 3.2. This is just the general form of a polynomial. Any rational zero of this polynomial is of the form p divided by q, where p are factors of our constant a sub 0, and q are factors of the leading coefficient a sub n. So if the polynomial p of x has rational zeros, then those rational zeros are going to be formed by taking factors of the constant and dividing them by factors of the leading coefficient. Okay. And what's important to remember and important to jot down here for notes is this rational zeros theorem. It gives a list of possible rational zeros. So the rational zeros theorem does not tell you what the rational zeros are. It gives you a list of possible rational zeros from which you can test to see which ones actually are indeed zeros. And what I mean by that is, here's an example. So we have a polynomial x to the third minus 4x squared plus 3x plus 8. We're going to use the rational zeros theorem to list all possible rational zeros. So according to the rational zeros theorem, factors of 8 would be our values for p. So the factors of 8 excuse me, are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Those are all the factors of the constant 8. Now q is the leading coefficient, so the factors of 1 are just plus or minus 1. The list that we actually need now is p divided by q. And what we do is we take one value of p at a time and divide it by one value of q at a time. Q could have more, for this particular example, q is just 1, which has one factor, plus or minus 1. But if q, for example, was 2, then the factors of that would be plus or minus 1, plus or minus 2. Anyway, we'll do an example like that here in a second. But if we took plus or minus 1 and divided it by plus or minus 1, we'd get plus or minus 1. Now if we take plus or minus 2 and divide it by plus or minus 1, we get plus or minus 2. If we take plus or minus 4 and divide it by plus or minus 1, we get plus or minus 4. And then if we take 8 divided by 1, we get plus or minus 8. This is what the rational zeros theorem gives us. This is a list of possible rational zeros for the polynomial p of x. This is not a list of zeros right here, because this is 1, 2, 3, 4. There's 8 numbers listed here in this list. And according to what we talked about back in section 3.2, a third degree polynomial is only going to have 3 zeros. A polynomial has as many zeros as it does the degree. So this polynomial can only have 3 zeros. There's 8 numbers here listed in this list, so not all of these values can be zeros. This is a list of possible rational zeros. And we're going to learn here in a second what to do next. Once we have a list of possible zeros, what's our next step? We'll talk about that in a second. So another one here to practice. Here's another polynomial. So 6 is what we use to find values of p. Factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Q here would be 3. Factors of 3 are plus or minus 1 and plus or minus 3. So now when we make our list using the rational zeros theorem, p divided by q, we take one value of p divided by one value of q at a time. So 1 divided by 1 is plus or minus 1. But then we have to take this 1 and divide it by the other value of q. So plus or minus 1 divided by plus or minus 3 is plus or minus 1/3. Now we move over to here. 2 divided by 1 is plus or minus 2, but then we take this 2 and divide it by 3, and we get plus or minus 2/3. Then we take 3 and divide it by 1 to get plus or minus 3. And then this one here, 3 divided by 3, that's just plus or minus 1, and we already have that here, so we don't need to repeat that one. Now 6 divided by 1 is 6, and then 6 divided by 3 is plus or minus 2, and we already have that one, so we don't need to repeat it. So this would be a list of possible rational zeros. This is not a list of the zeros, this is a list of possible rational zeros. Because again, p of x was a fourth degree polynomial, so it has 4 zeros. It can't have all of these values as zeros. Okay. Go ahead and pause it and write this down. This is a list of steps you're going to do to find rational zeros, and really this is finding, I'm going to change this to real zeros. So this is what you can do to find all zeros of a polynomial. So I should say polynomial. Okay. So first step we've talked about, make a list of possible rational zeros. The next step is incorporating what we talked about in the last lesson, section 3.3, division of polynomials. We talked about synthetic division, and you can use synthetic division to test whether or not a factor is a factor, or an expression is a factor of a polynomial, or if a number is a zero of a polynomial. So step 2 entails taking values from your list of possible rational zeros and using synthetic division into the polynomial to see if you get a remainder of 0. If you get a remainder of 0, you have found a 0 of the polynomial, and you continue that process until, well, sometimes it's easier to understand this process seeing the process rather than talking about it. So let's look at an example here. So we're going to find all the rational zeros, and then once we have the zeros, we're going to be able to graph this. So step 1 is a list of possible rational zeros, and remember that's our p divided by q. So factors of p are the factors of -4, which are plus or minus 1, plus or minus 2, and plus or minus 4. Factors of q come from the leading coefficient of 1, and that's just plus or minus 1. So then p divided by q is 1 divided by 1, 2 divided by 1, and 4 divided by 1. So that's plus or minus 1, plus or minus 2, and plus or minus 4. So that's possible rational zeros. Now step 2 tells us that we take each value from this list and use synthetic division to determine if it is indeed a 0. And remember from lesson 3.3, it's a 0 if we get a remainder of 0 using synthetic division. I'm going to start with positive 1 because that's the first number there on the list. And do the synthetic division. And right off the bat on our first guess, we got a lucky one. X equals 1 turns out to be a 0 because we have a remainder of 0. If we did not get a remainder of 0, we would have moved on to the next value and tested that one. But we got a remainder of 0. So if you read step 2 carefully, it says, when you get a remainder of 0, note the quotient you have found. So what we know, this tells us two really important things. What this tells us is, first of all, x equals 1 is a 0. And that also implies, or what that means, is that x minus 1 is a factor. And think back or try to recall from the discussion from 3.3, factors always come in pairs. X minus 1 needs to multiply with another factor, and that other factor is the quotient here. So x minus 1 multiplied by x, and this is x to the third right here, that's 1x to the third, minus, and this is x squared, so that's minus x squared minus 4x plus 4. And this is equal to p of x. This is the quotient. Okay, and step 3 says repeat step 2 with the quotient you have obtained in step 2. So this is the quotient that we obtained in step 2. So now we keep repeating this process of testing zeros from this list of possible rational zeros. But we only test them now on this smaller polynomial, or the quotient. So we've already tested 1, and we found one that x equals 1 works. So I'm going to use -1. But I'm going to use synthetic division now on the quotient, which is here. Call it 1, -1, -4, 4, and see if -1 is a 0. And that's not a remainder of 0, so I know -1 doesn't work. So I could try +2. Okay, so we have our remainder of 0. So what this means is now we found another 0, x equals 2 is a 0, which also means x minus 2 is a factor. And when we combine that with the factor we found in the previous step, x minus 1, and then this quotient here that's left over from the synthetic division is another factor, so that represents the factor x squared plus x minus 2. And this is what was mentioned in here, step 3. Repeat this process with the quotient you obtain in step 2. Continue this process until the quotient you obtain is quadratic. Once you've reached a quotient that is quadratic, you don't need to continue testing values from your list of possible zeros. So this quotient right here is a quadratic quotient. So now you can either factor this quadratic quotient using simple factoring techniques, or if it doesn't factor, you can use a quadratic formula. So x squared plus x minus 2 factors into x plus 2 and x minus 1. So we have all 4 factors now. We have all 4 factors of p of x. And if we wanted to condense this, since we have repeated factors, you could write this as p of x equals x minus 2, x plus 2, and x minus 1 squared. And the zeros are x equals 2, x equals -2, and x equals 1. And we talked about this back in section 3.2. This one has multiplicity of 2. And remember, the multiplicity is important when we graph this, which was what the next assignment of this question was to graph. Once we have the zeros, we can put those on as x-intercepts. So we have x equals 2, x equals -2, and x equals 1. Now the y-intercept, if we plug in a 0 for all of the x's here, if all of those x's were 0, you'd have 0, minus 0, minus 0, plus 0, minus 4. So the y-intercept would be 0, 4. Or sorry, 0, -4, because it was a -4 there. So the y-intercept is 0, -4. And the last thing that we did in section 3.2 when we graphed polynomials was to use end behavior, or degree, to determine end behavior. So the degree, this is a degree of 4, which means the end behavior, and it was a positive leading coefficient of 1. So that means the end behavior is right side is going up, left side is going up. So the left side is going up to positive infinity, and the right side is going up to positive infinity. We've got to figure out how these are going to connect there. So What we need then is to figure out the value of the graph there at -1. So if I plug in a -1 for all of these x's, I get -1 minus 2, that's -3. -1 plus 2 is +1, and then -1 minus 1 is -2. -2 squared is 4. -3 times 1 times 4 is -12. So -1 comma -12. So the graph comes all the way down to -12, comes up through the y-intercept, and then at x equals 1, since it had a multiplicity of 2, it's going to bounce, come down, and because there's no integer value between 1 and 2 to plug in, you don't need to plug in anything into the function to find out how far down it goes. It's going to turn up, cross through, and I know it crosses through here, and I know it crosses through here because these zeros didn't have the multiplicity. And there's our graph. So let's practice this again. Part B, same directions, find all the rational zeros and graph the function. So we start with P, which are factors of 6. So plus or minus 1, 2, 3, and 6. And then Q are factors of 2 right here, so that's plus or minus 1 and 2. So then P divided by Q is 1 divided by 1, which is 1. And then 1 divided by 2, which is 1/2. Plus or minus 1/2 rather. 2 divided by 1 is plus or minus 2. 2 divided by 2 is plus or minus 1, and we already have that one there. 3 divided by 1. And then 3 divided by 2 is plus or minus 3/2. And then 6 divided by 1. And then 6 divided by 2 would be just plus or minus 3, which we already have. So that is a list of possible rational zeros. We start then pulling numbers from this list and testing them with synthetic division. So I'm going to take 1, and see if it works. So do the synthetic division algorithm, and doesn't look like 1 works. So we test -1. Okay, it doesn't look like -1 works. I'm going to skip over the 1/2 for just fractions can work, but it's easier to test some of the whole numbers first. I'm going to do 2. Okay, so we have a winner, x equals 2. X equals 2 is a 0, which means, perhaps more importantly, that x minus 2 is one of the factors, and this quotient that remains is the other factor, 2x squared plus 5x minus 3. And this is equal to p of x. So now this process is actually going to be a little bit shorter now because the quotient that we have is already quadratic. So we don't need to go back to this list of possible rational zeros and test them on this quotient. We can go straight to factoring, or if it doesn't factor, we can use the quadratic formula. So to see if this factors, 2 times -3, there that's -6. We need factors of -6 that add to 5, so it's going to be 6 and -1. So we can use the factor by grouping process. So I can pull out a 2x there, leaves x plus 3, and then I can pull out a -1 there, and that leaves x plus 3. So then my factors are x plus 3 and 2x minus 1. So now I have three factors. I have the x minus 2, which I found from synthetic division, and then I have the x plus 3 and the 2x minus 1 we found from factoring, and this is equal to p of x. So then the zeros are x equals 2, x equals -3, and x equals, this one here, you'd have to add 1 and divide by 2, so you'd get x equals 1/2. None of the factors repeat, so none of these have multiplicity, which means when we graph these as x-intercepts, they're only going to appear, they're going to cross through. So we have x equals 2, -3, and positive 1/2. If we want to find the y-intercept, remember we let x equal 0. I actually prefer to do that using the general form to find the y-intercept. If all of these x's were 0, then we'd have 0 plus 0 minus 0 plus 6, which is positive 6. And then this is a third degree, which means the end behavior is right side up, left side is down, because we have a positive leading coefficient. So right side is going up to positive infinity, left side is going down to negative infinity. Now coming here, I know this is going to cross through. None of these x-intercepts bounces. These all cross through. And then -2 and -1, if we plugged in those values here, -2 for example, -2 minus 2 is -4. -2 plus 3 is positive 1. And then -2 times 2 is -4 minus 1, this is -5. So when x equals -2, this is all the way up here at positive 20. When x equals -1, we're at -1 minus 2, which is -3, -1 plus 3, which is 3, and then -2 minus 1 is -3. So that's all the way up at 27, so it goes way up there. Actually, you know what, hold on, -1 plus 3, that's 2, so it's 18. Okay, so it's not way up there, it's 18. It's just about right there, so it goes all the way up. 20 comes down, and then it comes down to 1/2, it crosses through, and then when x equals 1 right here, we have to figure out where the graph is when x equals 1. So 1 minus 2 is -1, 1 plus 3 is 4, 2 times 1 is 2, minus 1 is 1. So it's down at -4. And then it crosses through there. And that would be a graph of that polynomial. Okay, the next topic is real zeros of polynomials. So going back over here to this discussion we had somewhere right here. So real numbers consist of rational numbers. Those are numbers that can be written as fractions, like 1/2 or 2, because 2 over 1 is a fraction. But then another set of real numbers that are called irrational numbers. Irrational numbers are numbers that can't be written as a fraction. They don't have a decimal that repeats or that terminates. And those kind of zeros can only be found with the quadratic formula. Here's an illustration of what I mean. Rational zeros can be found by simply factoring x plus 3, x minus 2, for example. So then this graph would look like this. We have a 0 at negative 3 and a 0 at positive 2. So these are the zeros. And the parabola would look something like that. They're still technically real numbers because they're in the real number system and they exist on the x-axis, but they're rational numbers because they can be written as fractions, 3 over 1, 2 over 1. Real zeros that aren't part of the rational number system are going to be considered irrational. So x squared minus 6x plus 7 can't factor. We can't find the zeros by factoring techniques. So what we need to do is use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, where we follow the general form of a quadratic, ax squared plus bx plus c. So the opposite of b for this one would be positive 6 plus or minus the square root of b squared, which is 6 squared, or 36 minus 4 times a, which is 1, times c, which is 7, divided by 2 times a. So we have 36 minus 28 all over 2, and then that's 8. So the square root of 8 divided by 2. And then this is one of these Math 1010 topics that can become important in Math 1050. It's a skill that you need to be able to do, simplifying square roots. So the square root of 8 is equal to the square root of 4 times 2. And one of the properties of square roots is if you have a product underneath a square root, you can make separate square roots for each factor of the product. And then square root of 4 obviously is 2. So the square root of 8 turns into 2 square roots of 2. So this is 6 plus or minus 2 square roots of 2 all over 2. And then simplifying these can sometimes be tricky for certain students. So if you have a value here, here, and here, if you have a value in all three of those spots, once you've simplified a square root, numbers inside, you can't mess with them. Once you've simplified a square root fully, there's nothing that's going to happen with that 2 inside the square root. So again, if you have a value here, here, and here, if you have a number in all 3 spots that have a common factor, then you can simplify those 3 by their common factor. So this would be 3 plus or minus 1 square root of 2, or simply square root of 2. And you could put divided by 1, but again, dividing by 1 doesn't do anything. So you'd have 3 plus or minus the square root of 2. So those are the zeros. The zeros are x equals 3 plus the square root of 2, and x equals 3 minus the square root of 2. Now the square root of 2 is approximately 1.4, so this is approximately 4.4, and then 3 minus the square root of 2 is 3 minus 1.4, or approximately 1.6. So they're still real numbers because they can be graphed, they can be put on a number line, but they're just not rational numbers because it can't be represented as a fraction. So we can still graph those as, let's see, what were they, 4.4, 1.6. So 4.4, 1.6, those are the 2 zeros. So we still have a parabola with real x-intercepts. So the difference now in this topic is once we get to that step in finding zeros where the quotient is a quadratic quotient, it may look something like this that can only be solved with the quadratic formula and not by factoring. And that's the only difference. The process is still the same when we're finding real zeros. So an example, we have a 4th degree polynomial. So it's going to start the same way. We need to do p divided by q. And just for sake of time, anytime q is 1, dividing by 1 doesn't change any of the values in your numerator. So p divided by q, when q is 1, is really just your list here for p. So the factors of 10 are plus or minus 1, 2, 5, and 10. Okay, and then we do our synthetic division. So 1 doesn't work. We didn't get a remainder of 0. So we can try negative 1. Okay, that didn't work either. So we can try negative 2. Okay, so we found one that works. So x plus 2, and then we have the quotient here, which is x to the third minus 7x squared plus 9x plus 5. That's equal to p of x. So now we continue synthetic division on the quotient, or on the smaller polynomial. And the reason we have to keep going with synthetic division is this is not a quadratic quotient yet. So we can only stop doing synthetic division once we have a quadratic quotient. So I've already tried 1 and negative 1. They didn't work. Let's go to 2, positive 2. But using the quotient now here, it's going to be 1, negative 7, 9, and 5. Okay, 2 didn't work. So we can try 5. Okay, 5 worked. So x minus 5 is a factor, along with the factor we found in the previous step, which was x plus 2, and then we have this quadratic factor of x squared minus 2x, 2x minus 1. Okay, now we have a quadratic factor. And remember, once we have a quadratic factor, we don't need to go back to the list of possible zeros and use synthetic division. We can now either factor this, or if it doesn't factor, it's going to give us irrational zeros using the quadratic formula. X squared minus 2x minus 1 does not factor. So we need to find the zeros using the quadratic formula. So the opposite of b, plus or minus, the square root of b squared, so negative 2 squared is 4, minus 4 times a times c, all over 2 times a. So 2 plus or minus 4 plus 4, which is 8, all over 2. And we already had seen that the square root of 8 is 2 whoops, 2 root 2. So the square root of 8 is 2 root 2 all over 2. And again, only if you have a number here, here, and here. They have to have a number in all 3 spots that share a common factor. So 2, if they're all 2, then obviously they share a common factor of 2. So they can all be divided by 2, which would give us x equals 1 plus or minus 1 root 2, or just simply root 2 all over 1. But again, dividing by 1 doesn't change the value. So x equals 1 plus or minus root 2. So the directions here, actually I didn't have them written. The directions here would have just been find all zeros. This one wouldn't have been graphed because we ended up with zeros that were irrational. And typically you don't graph if you have irrational zeros. So if we were to list p of x now in fully factored form, so p of x was x plus 2, x, what was the other one? X minus 5. And then we have 2 other factors that come from this 0 right here. And I see students often struggle with these kinds of zeros, writing them as factors. So I'm actually going to write this as 2 separate zeros. X equals 1 plus the square root of 2, and x equals 1 minus the square root of 2. The way that you make factors out of these is you just move all the terms over to the same side of the variable. So if I subtracted 1 and subtracted the square root of 2, now that's my factor. So x minus 1 minus the square root of 2. And then here, if I subtracted the 1 but added the square root of 2, I'm going to have x minus 1 plus the square root of 2 equals 0. So that's my factor right there. X minus 1 plus the square root of 2. So those are the 4 factors of p of x. The zeros are x equals negative 2, x equals 5, x equals 1 plus the square root of 2, and x equals 1 minus the square root of 2. So the homework may ask for just the zeros, or it may ask for the zeros and the factored form of the polynomial. And that looks like brings us to the end of lesson 3.4, finding zeros, real zeros at least, of polynomials.